Hello, a very warm welcome to everyone, and thank you for joining us for the first in our new series of webinars for 2021. My name is John Norman. I'm Head of Marketing at Optibrium and moderator for this webinar, From Similarity to SAR, in which we'll be demonstrating interactive navigation of similarity relationships to guide optimization. So now it's time to hand over to our presenters for today, who are Matt Segall, CEO at Optibrium, who will host today's webinar, and to Peter Hunt, our Director of Computational Chemistry. Matt, I will now hand things over to you.
Thank you very much, John. Thanks for your kind introduction. It's a pleasure to see so many familiar faces in the audience today, and also some new people, so we hope you enjoy the presentation and demo today. Before we get started, it's my pleasure to introduce you to my colleague, Peter Hunt. He's our Director of Computational Chemistry here at Optibrium. Before joining us, he had over 20 years of experience in pharma, both in American Co. and Novartis, where he latterly led the UK CAD group in Novartis. He has a wealth of experience in practical drug discovery and is going to be leading the majority of today's presentation and demonstration of some of the ideas that we're going to share with you today. But before we get started, Peter, based on that experience over many years and many different methods and different types of projects, I wondered if you could share just a little bit about your experience of the potential pitfalls and how software can help in the analysis of structure-activity relationships.
Yes, Matt, it's one of those unfortunate things for this particular topic is that it's easy to say, but actually quite difficult to define to everybody's satisfaction. I mean, any small molecule-based research project, whether it's pharmaceuticals, agrochemicals, or flavors of fragrances, is predicated on the belief that similar things work and behave in similar ways. And it's just that thought of how on earth do you define similarity when you don't necessarily fully know what your target is, what preferences and what features are important. And so we all know about the methyl, magic methyl, that is there just to change conformations of small molecules. You can get just small changes like in flavors and fragrances. The epimer at a particular center can have a dramatic effect on the properties that people are interested in. And so it's that definition of similarity which gives you the neighborhood effect, which you can then work out what it is that is important to you. And similarity, that I would say, is really in the eye of the beholder.
Well, I think that's a really nice introduction to some of the challenges we're going to be talking about today. So I'm just going to say a few words of introduction and introduce some of the concepts that we'll be looking at. And then I'm going to hand over to Peter, who's actually going to show you some of these ideas in practice. So I'm just going to start by actually addressing the challenge that Peter just mentioned and the many different measures of similarity we use in the analysis of SAR, and then really focus on a number of different applications to understanding structure-activity relationships, things like clustering and R-group analysis, activity cliffs and landscapes, matched molecular pairs, and so on. I'll also give a quick introduction to how we can explore these SAR relationships in a very interactive way using the card view approach in our StarDrop software. And that's just going to be a quick introduction. And then I'm going to hand over to Peter, who's actually going to show you some live examples of how this works in practice. Of course, as John said, we'll also come back at the end and answer any questions that occur. So please feel free to type them in, and we'll be happy to address those in the Q&A session at the end. So as I said, Peter just introduced the challenge quite nicely. We have many different ways that we could define similarity in a computational sense that capture these sorts of effects that Peter was describing. So things like fingerprint similarities, they can be sort of path-based fingerprints or max keys, and we typically use various sort of abstract indices like Tanimoto indexes and so on to give us a measure of similarity. We also look at similarity in properties, often in terms of sort of descriptor space and distances within those descriptor spaces. Often, I guess a natural way to think about whether two compounds are similar is to say, well, they have a very large common substructure. They share a lot of their structure, or perhaps are based around a common scaffold. And of course, we often think of a very widely used concept of match pairs. These are compounds that are essentially identical, except for one small substitution at a single position. And the appropriate measure of similarity really depends quite strongly on the particular question you're trying to ask about your chemistry and the properties in which you're interested. So, depending on what method we want to use, there's lots of ways we can approach the understanding and visualization of similarity. One very common approach is clustering, so grouping together compounds that are similar according to our chosen definition. The goal here is to identify groups of compounds with particularly good activity or good properties, or interesting SAR for greater exploration. Here on the right-hand side, I'm just showing a visual impression of that sort of clustering. This is using sort of a chemical space visualization, or you can look at property distributions in terms of the different clusters. And here you can see a particular cluster that has, at least on average, the higher activity. So this is a very nice way to find those sort of regions of chemical space or clusters of compounds that are worth further investigation. But one of the big challenges is that a cluster defined computationally often does not really correspond with what you might look at a compound and say that they're the same or they belong together in some way. So it doesn't really necessarily agree with your interpretation of, say, a chemical series. Another very common approach is to look at sort of R group analysis. So here we can take a common scaffold and look at different substituents on that scaffold, often called R groups. And here what we're trying to do is to find trends in R group properties that can guide further optimization. Maybe you need a hydrogen bond donor at one particular position, or a particularly lipophilic group in another region, or something like that. So this is a very nice way to look at sort of patterns across a chemical series that share a common scaffold. It's often quite manual setting this up. You sort of define your scaffold and the different substitution points. It can be a bit tricky to set up. It's a bit of a challenge, particularly when you're trying to consider variations in linkers between, say, different ring systems, or even variations within a scaffold. And so we need to think very carefully about how to make that as easy and as seamless as possible. Another example we'll see is the idea of activity cliff detections. Activity cliffs are small structural changes that result in a big change in activity or another property. So here you can see very similar compounds, pairs of compounds, and the differences in their properties, so that you can find those changes that drive a particularly big increase or decrease in a property of interest. This helps us to explore nearest neighbors to a particular reference compound, a compound of particular interest, and see if that guides us through the optimization and particular changes we might like to consider. A variation on this is the so-called Structure Activity Landscape Index, or SALI. This sort of weights the change in property, so the absolute difference in the property, by that similarity. And so again, here you can see it highlighted in red are those biggest changes for the smallest, biggest changes in property for the smallest change in structure. Now, this is looking at the similarity of a number of compounds to a single reference, a particular compound of interest. That can then be generalized into a more complex analysis. Here looking at, we describe as an activity landscape. This is something that was popularized by Jürgen Beyerath and his groups. And here what we do is we compare each compound with every other compound in a particular data set, and we look at groups of compounds that share a high degree of similarity. And what we might do is look for regions that are particularly rough, where there are large changes in an activity from small changes in structure. So you can see some examples here where there's particularly sort of active compounds embedded within sort of a less active space. That indicates some interesting SAR. There's another example here. Conversely, you can find flat spots. So here's an example where there are very small changes between the activities within this group of compound. That, on the negative side, indicates a limited opportunity for optimization. There's lots of different changes that have been explored and very small changes in activity. On the positive side, that might give us an opportunity to optimize other properties without having a negative impact on activity. If we already have lots of active compounds in that region, it gives us flexibility to vary physicochemical or ADME properties, for example. And then I mentioned matched molecular pairs. So these are comparisons between compounds that differ only by one small substitution. And here our objective is to find replacements, often represented as transformations between one group and another, which have consistent and significant impact on an activity or other property. So what we're trying to do is find patterns in our data that suggest that a particular replacement will give us a consistent impact. Here you can see, for example, that the change from a hydrogen to a chloro substituent, if you look at the distribution of properties here for the pKi, you can see the vast majority of that will actually decrease the pKi, so indicating that perhaps if we have a hydrogen, we might want to try replacing with a chloro or avoid adding a chloro at certain positions. The challenge with this is, particularly if you're looking at quite a diverse data set, is that matched pairs are often very context dependent, particularly for target activity, which can be very sensitive to particular sort of binding modes, or particularly if you're looking across different targets, it's very hard to translate that sort of SAR from one target into another. So you need to ask the question, well, if I can see this consistent pattern, where does it apply, and where are the exceptions that actually prove that rule? So we've just gone through very quickly a number of different approaches to use similarity to extract information about the structure-activity relationships in which you are interested. And so some of the challenges of actually using this in practice is, well, how do we actually organize the compounds we're looking at and the associated data to reflect the way we're thinking about them? We want to do this in a very interactive and intuitive way so we can explore these different results and represent the output of these complex analyses in a way that's easy to interpret and, more importantly, act on the output. We don't just want to look at these, we want to learn from them and think about what's the next step in optimization. And here it's about combining the strengths of the algorithms to analyze these very complex data sets, lots of different properties potentially, and lots of different variations in structure, but also the knowledge and understanding of the expert. You understand your chemistry, you understand the biology and so on, and you really want to get the most from that combination. And finally, we want to be able to share and present these results very, very easily. It's all great to explore it yourself, but you want to create a presentation perhaps to share those results with your colleagues in your team, or create a report that you can send and share with others. So it needs to be very flexible and be able to represent the sort of different viewpoints of different disciplines who are interested in looking at the data in different ways. So the last concept I'm going to introduce here is something we call card view, and you'll see some examples of this in a minute when I hand over to Peter. But this is really about breaking away from the constraints of the sort of conventional chemical spreadsheet that we work with. You know, a chemical spreadsheet is just a big long list of compounds and associated data. And while that's a great way to get an overview of a data set, it doesn't really represent the way we're thinking about the compounds in the context of our project, and in particular, that structure-activity relationships. We want to represent those compound relationships in a more natural way. So what you'll see is that in this view, compounds are represented by these little cards that can put whatever data you want on them, whatever's most relevant to you, and then you can move these and position them however you want on essentially an infinite desktop. We can also think about groups of compounds in terms of stacks. So we can group these compounds up that belong together in some sense, and we can look at the distributions of properties across those different groups. So here you can see a histogram showing the distribution of affinity, or there's a box plot showing the distribution of log p, and easily compare across these multiple properties in which we're interested. And finally, another thing you'll see are links between compounds. So links represent that relationship, and on those links, you'll be able to highlight big changes or key changes in properties to really draw your attention to those most interesting results. And so what Peter is going to demonstrate now is how we can combine this sort of approach with these different algorithms that I've just outlined to really help us to understand, visualize, and act on the structure-activity relationships in our chemistry and data. So with that quick preamble, I'm just going to hand over to Peter, give him control, and he's going to take us through some practical examples of how these approaches can be applied. Over to you, Peter.
Thank you very much, Matt. And just to check, I hope that you can see open StarDrop project.
We certainly can, Peter. Thank you.
Okay, terrific. Well, welcome everyone. The scenario I'd like to paint for you today is that you are the new chemistry team leader who's been asked to contribute to this PPAR Gamma project. Therefore, your task, before your team starts working on anything, is really to get to grips with some of the SAR that this established project has already created. So I've opened up the project data file here, and we have a dashboard that shows us some visualizations on the right-hand side, just a histogram of the activities of the compounds within this data set. And you can see that it covers 5 orders of magnitude here. And anything that's sort of in a reddish hue is the poorly affine, and anything that's in a yellowish hue is the really active compounds. And on the left-hand side, we have our visualization tab where I'm just plotting log P versus PIC50. You can see that there is an unfortunate correlation in terms of a trend that the highly active compounds do happen to be the most lipophilic. But lipophilicity isn't the be-all and end-all. It is necessary but not sufficient. In the middle here, we have a chemical space. And this chemical space is what Matt showed you earlier, where the points in this plot are all the compounds in this data set. And we use methodology called TS&E to do that dimensionality reduction of the descriptors, the topological and whole molecule descriptors that we have within StarDrop. And we reduce that down to 2 dimensions. And so compounds that are similar to each other appear close to each other in this chemical space. So here we've got a couple of azarindols. And in this particular place, these are different structures. These are, aryl sulfonamides in here. And so what one can take from this particular plot is we have yellow blobs in a number of areas. So we've got quite a few islands here which indicate different chemotypes. And we have activity distributed across those chemotypes. So this is structural similarity. But if I just show you that actually a chemical space plot can be created from properties. We provide a launched drug space, which is on 1,300 compounds. And you can see the distribution of the points within this data set look completely different when plotted in a launched drug space compared with a chemical space, which is created only using the compounds in my data set. But you'll notice also in my table on the right-hand side, I have a few columns of green values here. These are sort of calculated properties. And I could use those properties to define similarity. So I can define a property space. All I need to do is just go under create, give it a name, choose properties, and then I can select which properties I want. So this is the property space created from the compounds in that data set. And again, nice to see that in this data set, it's not just a single property or collection of properties which is giving activity. We've got yellow points distributed across this space. This gives us some confidence that we'll be able to change these molecules, come up with compounds that would be backups in this particular project. And just to illustrate the fact, if I circle around some of these active compounds here, right in the middle of this chemistry space, you can see the neighborhood behavior in property space is very different. So again, this definition that I mentioned right at the beginning, what is it that drives similarity? Now, we can provide you with the chemical space that comes from our own StarDrop descriptors. You can generate your own set of properties and then use those to define the chemical space, the property space that is important to you. So this is the overview of this data set. It gives you a real sort of top view of the whole data. What I'd like to do now is really go into more of a chemotype view. Now, of course, I've said that similar compounds are similarly clustered together in this chemical space. And so I could define a chemotype just by ringing around these compounds and saying, right, that's my selection. That's going to be one chemotype. But that can get a little bit tedious. So what I'd like to show you is the clustering that we have within CardView. Here is CardView, and each of the cards is colored by its activity and just laid out in a nice big grid. So under Analyze and Clustering, what I'm going to do is choose the common substructure. I can define a similarity. In this particular case, I'm just going to go for a fairly low value-ish of 0.5 and hit Cluster. And what this is doing, it's taking our StarDrop fingerprint. It is looking at the similarity between those common substructures that it finds, and then lays them out in CardView in a way where there are some neighborhood effects. You'll notice on the right-hand side here, I've got a Billy No-Mates type of singletons. This is just placed on the map. I'm just going to draw it in here so that I can expand and investigate what sort of structural clusters I've got within this data set. Again, the colors on the cards are representative of the activities underlying the stacks. And if I just focus in a little bit on this set, you can see that what we have here is a sort of consistent phenyl oxazole unit. And this is sort of illustrative of something that Matt was talking about. We have just used the computer to do the heavy lifting to say, right, give me some common substructures within here. But actually, there is a commonality amongst all of these in terms of that phenyl oxazole. It's just a linker change between that and an aromatic. So it may be that actually what you would like to do is take these stacks and put them all together. And that's certainly something one could do. The colors of these stacks represent those average values for activity. And what you can see is this extended ether linker seems to have much better distribution of activities compared to the others, because this is the yellower cards, yellower stacks, higher activities than you see in these. At the moment, I've got a stack design which just gives me the common substructures. But under design, I can actually give me a lot more information about the contents of that stacks. As Matt said, we could put in there histograms And so you can see that this stack, yes, it does contain a larger proportion of more active compounds in here compared to these other stacks. And have a look at the distributions of other properties, or in this case, I've just got a representative structure from this stack. And as I said, I can just take these stacks, drop them on top of each other, and I can see how those properties change as I do that stacking. So if I'm looking at an overall set of distribution of properties for particular series that I can define, this is a nice way of doing it under the design menu. For the moment, I'm just going to go back to the structure, and now you can see that it's calculated that common substructure of just what I wanted, the phenyloxazole. And if I just go down to a little interesting comparison here, obviously the yellow cards are of interest to us because these are the highly active compounds. But it's interesting the neighborhood behavior of this clustering enables us to see that actually what we have here is this benzylic substituent and the ketone, or amide in this case, but it's flipped round. This unit here, really, indole, is not acting directly. It seems to be a scaffold because we have derivatives within this set which flip over the pyrrole ring of an indole, and it's still as active. So nice little nuggets that one can get from doing the clustering. If I go to find match pairs, I'm just going to look at the match pairs of all the compounds in this data set. And I'm going to link the cards, these compounds, by the change in the PIC50 value. So anywhere where you have a large change, you'll see a red linker. Anywhere you see a gray linker, well, there's no change. And whilst matched pairs analysis is a very compound to compound view of the data, what I'd like to show when this comes up is you can get a lot of information about the general nature of the SAR and the work that's been done in a particular data set by running analyses such as these. With the clustering, that gives us the ability to manually control what sort of chemotype definitions you could have. So you're defining similarity by that substructural features. With the matched pairs analysis, it gives you that overall view of the data set in terms of how much work has been done on the chemotypes, on the compounds within this data set. I also like to show this really because it can look a little scary. When you have large data sets, you can have very large networks of compounds. And people tend to shy away from just looking at these because they look like immense spider's webs on the screen. But I would encourage people to look at these matched pair neighborhoods, matched pair plots, and be able to take information from them. So here it is. The matched pairs analysis has been done. Again, the cards are colored by their activity. So as I described, you can see that there are networks here that are larger than others. You can see quite easily where you've got activity cliffs, pink cards connected to yellow cards. These are where activity has changed quite dramatically. You can also see that there are areas here containing all pink cards. Obviously, these particular compounds, and in this particular case, it's those aryl sulfonamides that we showed in the chemical space before, they've had a bit of work done on these, and they haven't really found any success. Here is a series that we can push to one side. As Matt mentioned, you can get networks where you have the other sort of flat SAR. Here we've got a network where we've got all yellow cards. Wonderful. This should be something where you can change the structure and not change the activities. This could be something where you would be directing your efforts. However, that is slightly context dependent, because if, say, this was a high throughput screening set and you were doing the same sort of analyses, one might be suspicious of networks such as this that have only got active compounds, because are these networks indicative of some structural feature that is giving you assay interference? In this particular example, that's not the case, but the networks and the analysis that we can provide in this case can give you other indications, other views and impressions of a data set. On the left-hand side here, I show our matched molecular pairs output. This was some of the dialogue that Matt was showing in his slides. And again, at the moment, these are sorted by the transformations and the frequency of which those matched pairs actually exist within this data set. I can click on any of the columns that are here, and this is the change in PIC50, and selection of any of those links will actually take me to the cards, and we can see that in this particular case, we have a huge change, 4 orders of magnitude change, that comes from a simple epimeric shift. This is important as far as I'm concerned, because if a simple epimeric shift has this effect on the SAR, then what other changes have been made in the epimer that is poorly active? Because if you've made changes and all of those compounds are inactive, well, it may not be to do with the other parts of the molecule. It may only be due that you've chosen the wrong epimer. In certain cases, these have been known as innocent bystanders. But it is something to be wary of, that if you're looking at SAR and interpreting the structural changes and say, oh, well, I've made changes here and it's not improved anything. If you've got something that is this dramatic in terms of the activity difference, it will have an effect. If I just scroll down through this set of match pairs just to illustrate something else that Matt mentioned, the interpretation of matched molecular pairs is really context dependent. And so if I pick on this hydrogen to isobutyl change here, we've seen it 3 times within this data set. And here are the 3 examples. One example, detrimental. One, well, pretty well no change. But one, highly beneficial. So what is it about this particular change that's had an effect? Where it's been detrimental, it's in the para position of this phenol. Where it's had little effect, oh, it's also in the para position. Why is that one no effect, but the other one detrimental? And with this, one can see that actually you have a thiazolene dione here, which is a meta relationship to the rest of the unit. But in this, it's a para relationship. So not all SAR, not all changes are equal. What happens when it's beneficial? Well, actually, that isobutyl unit is not on the para position of that phenol chain anymore. It's now within the chain. And so there's a different location for that change. Something you should look at when you're looking at matched molecular pairs and just trying to interpret the average changes. See what the actual specifics are, because they will have an effect. So, what I'd like to do now is just focus in on a particular card and have a look at the activity around it. So I'm going to use our find option. And that will locate the card. And then I will actually use the match pairs neighborhood. Again, I'll copy it around. I'm just going to get rid of, hopefully, that glowing molecule. But here is the card that I've chosen, and it is these form of the phenyl sulfonamides, but this card has decent enough activity. We can see that we've got short red arrows indicating the activity cliffs. And here the difference is this methoxy group versus a hydrogen. The next one around, methoxy group versus the methyl. Perhaps there is something about the hydrogen bond accepting properties of this substituent which is giving you activity. Looking at some of the other derivatives here where we've got the ketone or the amide, yes, that could be the case. But all is not well in terms of hydrogen bond accepting if you've got too much, as in this acid or in this sulfone. Then you get red arrows. You're getting a lack of activity. And so this match pair neighborhood gives you the ability to look at a particular structure and work out what are the changes that can be made around it, what could be giving you activity, and what maybe where you shouldn't go. That as match pairs. And match pairs are, of course, just a single change. If I just take a slightly different compound and look for that, you'll notice that this particular card and this compound looks remarkably like the other one, and yet it's not in that neighborhood, essentially because there are more than one change happening on this structure. And to accommodate those, we have activity, either landscapes to do the whole data set, or neighborhoods will just to look around a single compound. And so again, all of the compounds within this data set are arranged in a spiral around our reference. The most similar close to it, and again the colors of the cards and the colors of the links show you this activity cliff, because these are red, indicating the difference, 2 orders of magnitude difference here. Now here we have the acid again that we saw previously compared to the ester. So perhaps it's just charge here. Hydrogen bond accepting functionality, that could be giving us the activity. It wasn't picked up in the match pairs because we're comparing a monochloro and a dichloro. But still being able to do this analysis quickly gives you the impression of what are the structural features around these molecules that can affect activity. So these are nice, easy ways of being able to get that compound to compound comparisons. But one other way that we have is an R group decomposition. And so I'm going to select this reference again and just start the R group decomposition. It's easy to go through and define that is my scaffold, but I realize there may well be other substituents on this sort of scaffold. I've got 3 already listed there, but just in case you've got other substituents, I can just add them in. You'll also notice that this particular structure has symmetry. So R1 and R6, R4 and R5 are symmetrical. This could cause problems to other R group decompositions. But in our R group decomposition, we try and maximize the consistency in the substituents that occur at those positions. Because we're in card view, nothing much seems to happen. But if I go back to the table view, you'll now see that we have introduced the R groups associated with that particular substructural definition. You'll also notice that I've got a whole heap of blank cells here. If it doesn't contain that substructure, it doesn't provide an R group. So the easiest thing is just to sort ascending. No, I won't do that. And it brings all of those R groups to the top. If I go back to the visualizations, I can select any particular column and it shows me what are the substituents, what are the R groups within that column. I notice that R4 and R5 here, they're all always unsubstituted. And so I can just select those and delete. We have automatically, because it's looked at R1 and R2, the SAR plots that Matt was describing before. So you can look and see what are the variations, what are the combinations that have happened within this particular chemotype. And indeed, some of the features that we have under the R group decomposition tool is an enumeration functionality. And that will go through an R group decomposition and fill in all of the molecules that you have not yet made, so you can evaluate them to see whether they would be suitable compounds for making. If I'm just going to select a single column, you can see the frequency of each of the R groups in that. If I choose R2 here, you can see that I've really just looked at the chloropyridine. But if I go to a scatter plot, and plot the PIC50, and I'm also going to change these so that you can see the size of these points a little bit larger. Here is the distribution of activities for each of those R groups. It wouldn't be nice to know what would be the effect of moving from the chloropyridine to the quinoline. One of the new features that we have within StarDrop 7 is that we can customize plots like this by drawing lines between the points that have the same value for other property columns. So in this case, where the R1 substituent is the same between variations in R2. And what I can do is to zoom in on this. And you can see now in changing R2 from the pyridine to the quinoline, most of the time it's not a good move. But there are some other aspects here which look as if it should be acceptable. As it happens, I've zoomed in so much that actually the activity differences here are quite small compared to the variations in the assays. But it illustrates the fact that you can do this change and illustrate the effects of changing R groups on a particular scaffold using the R group decomposition and the customization of lines to join those which have the same elsewhere. So these are the general SAR interpretation tools that we have within StarDrop. One of the things that I would like to mention just as before we hand back to Matt is That's good to be able to look at SAR and be able to say, ah, yes, this is the SAR within the set. But even better to be able to use that SAR to make suggestions for new compounds to make. And one of my favorite applications within NOVA, which is our novel molecule generation module, is matched series analysis. And in matched series analysis, you can go through the SAR within your data set, look at the SAR trends, and use those trends to find other R groups, either from within other chemotypes in your SAR, in your data set, or from knowledge bases outside of your data set, and make suggestions for which compounds should be made that would have increased and improved activity. I have done that analysis in this particular case, and so here is a data set of suggestions that comes from cross-series SAR. I've done this match series analysis against my own data set, and I've used the SAR from one series to suggest compounds that I should make in a different series. Here is what we have on the left-hand side. The suggestion is shown in the top, based upon the SAR trend that is listed on the top of this table, and it forms a very similar SAR trend to one of my other chemotypes in the data set. Again, a thiazolidinedione. And therefore, one of the things that hasn't yet been made is this biphenyl. It may be something that you dislike. It may have other properties which may not be ideal, but the suggestion is there, and it's based upon the SAR that you have within your data set. One of the consequences of doing these type of SAR analyses is, as you may see in this, where you've got red as being least active, yellow the most active, this chloroderivative in this chemotype seems to be odd. So is this a dodgy data point? Is this something where it just happened to crash out of solution, stick to the size of the flask, and therefore gives a data point that is actually incorrect? And that will affect your interpretation of the SAR within your set. So thank you very much for attending and listening. That is what I had to describe, and I will be handing you back to Matt.
Fantastic. Thank you very much, Peter, for a great tour of lots of different ways to look at your data, lots of different ways to understand that SAR. There we go. So hopefully you can see my screen okay. And what I've just mentioned before while lots and lots of questions coming in, thank you very much, to give you a chance to type, I'll just mention that for those of you who are familiar with StarDrop, you'll have seen some new features that you hadn't seen before. And that's because we are just about to release a new version. It should be arriving any day now, later this week. This is StarDrop 7, so a major new release. One of the things Peter demonstrated was the matched molecular pair neighborhood. So this is a new feature to look at all the matched pairs around a single compound, as well as those nice line plots for analyzing matched pairs by R groups. We're talking about the reaction-based library enumeration in our next webinar, integration with our new Sorella platform for deep learning imputation in drug discovery, a completely new approach to filling in the blanks and getting value from your data, and lots of other enhancements, too many to go through here today, but hopefully you'll see that announcement coming out in the next couple of days. So without further ado, I can see many of you don't need to be shown how to ask questions, so that's great. But those of you who are not familiar, just a reminder that you have a question panel as part of the GoToWebinar platform. If you type in the questions here, they will appear here on my control panel. And what I'm going to do now is start to work through some of those. And a combination of Peter and myself will be very happy to answer any questions that you have. So let's get started. One question here is, what kind of algorithm is used for clustering by common substructure? Can you take that one, Peter?
Well, I mean, the essence is trying to find the common both atom type and bonding that is there, and try to create the maximum common substructure that one could find, and then compare that common substructure between the two molecules and others that you find. If there is a commonality between those two that is greater than the similarity threshold that I put in my case 0.5, then they will be clustered together. But that's what I would be describing. Matt, can you provide a little bit more if they want additional detail on that?
Yeah, absolutely. So the common substructure is a graph similarity method. So we're looking at finding the maximum overlap of the graph between the two compounds. There are some neat tricks you can play here, though, because if you're looking at a large data set, doing a graph similarity between every single compound can be very time consuming indeed. So we can do an initial pass of just looking at a sort of a Tanimoto similarity. If two compounds are too dissimilar, their common substructure is going to be quite small. And so you can sort of play some neat tricks to speed that process up. There are other similarity methods that can be used for clustering as well. So we can look at a Tanimoto similarity based on path-based fingerprints, or actually similarity in any descriptor space that you want. So you don't have to use common substructure. There's lots of different ways that you can cluster your compounds and generate those stacks of cards, as Peter showed you. All right, here's another really good question. So looking at pairs of molecules and cards, is there an option to get the molecules aligned to their common substructures and make that visual inspection easier to see where the change has happened? Peter, do you want to take that?
The answer is yes, in the sense that we do have the capability of picking a card or picking a compound where the alignment is the way that you'd like it. And then it's a simple right-click function to say, align the cards to this one. And therefore, the structures will be reorientated to provide a consistent an overlay or consistent visual view of those particular structures as possible. Now, obviously, if the compounds are too dissimilar, then that alignment is not necessarily accurate. But for all of the compounds that are highly similar, then you will get a consistent alignment between the structures. And it is certainly something that we have in place, or have in our list of enhancements to provide that structural clue as to what the common substructure happens to be between two cards. Obviously, there are a few other things, nuances that one would like to be able to provide to the user. Sometimes it is the common substructure that is important. Sometimes it's actually highlighting the difference that is most informative when looking at a pair of cards. And so these are the sorts of features that we hope to introduce in other versions, later versions of StarDrop.
Thanks, Peter. Okay, we've got another question which has come in a couple of different forms. So this is about looking at transformations not just of R groups during an R group composition, but actually changes in a core, or when you have multiple cuts, so maybe looking at changes in a linker or something like that. And so the answer to that is, yeah, absolutely. Peter showed a relatively straightforward R group analysis around a common core, but you can have actually multiple distinct regions of the compound that are in common and look at changes at sort of linkers or ring systems linking the two different or multiple different regions. Also, you can actually have what we call X groups, so fragments within the core that change, and you can look at how those changes in those regions can actually influence a property. And finally, you can actually do what we call a multi-core or multi-scaffold R group analysis, where you have different scaffolds that you believe have a sort of a common binding motif, And you can look at the commonality or the differences in the SAR between those different cores as well. So there's an enormous amount of flexibility and far more than you could demonstrate in just a few minutes in the middle of a demo. I should say on our website, on our online community, there are a number of videos that illustrate things like multi-scaffold R group analysis and looking at variable linkers or variable ring systems as well. So please do have a quick look and you'll see lots of examples of that. Okay, so there are another couple questions here that are in common about where you get the data from in the analysis or to perform the analysis, and particularly, can you actually link with databases? So again, I'll answer that one very quickly. You can load in data from pretty much any source that you want, so standard file formats like SMILES and SD files and so on. But absolutely, you can also link StarDrop directly with your database, support almost all different database architectures through what we call our query interface, so that you can perform a query from StarDrop and bring your data directly in, ready to go, pre-formatted and ready to do the analysis. You can even do what we call a refresh. So once you've done all this lovely analysis that Peter demonstrated, of course, time moves on, more compounds are synthesized, more data are available. And just with a click of a button, you can actually go back, retrieve the latest data, merge it in with your existing data set, and immediately those sort of visualizations and analyses update so that you can see the impact of that new data on the analysis that you've done and the SAR that you're looking at. All right, I'm aware that we're running a little bit low on time here, but here's a good question. So Peter, I think this relates to the match series analysis, which you demonstrated right at the end in terms of SAR generation. Does it work for phenotypic screen results as well as sort of simple biochemical assays to make suggestions for new molecules?
Well, the complications with the phenotypic screens are that you don't have the simple direct relationships between a structure and its activity at a particular target, and therefore you are having the structure and the changes in the structure play different roles. So being able to get cellular absorption, solubility, actually getting to the site of action, whether that happens to be then a multiple site to create the phenotype that is seen within the screen. And so the more that you move away from that direct compound to target binding and the effects of structure on that, then it becomes more difficult to really have that interpretation. However, if you happen to have a knowledge base that is created from structural series that are also tested in that phenotypic screen, then one would hope that, again, the SAR that is giving you that activity in that phenotypic screen can be transferred. And so I see no reason why not, if your knowledge base is really appropriate to the measurement that you're trying to make.
Yeah, absolutely. I think that's one of the big advantages of match series analysis is that it's transferable between different targets. So you don't necessarily need to know the specific target you're working with, provided that activity is driven by a sort of a common mechanism in your phenotypic screen. So yeah, that's a really interesting application of that. Okay, so I think we're just going to do one or two more before we wrap up. So there's a nice question here. Can you actually combine analysis on compounds that have already been synthesized, as you just showed, with those that have not yet been synthesized? And again, just to answer that, absolutely, we were focusing here on SAR for compounds that have been synthesized and tested. But StarDrop also provides a very comprehensive range of predictive modeling capabilities, interactive design, de novo design, and library enumeration capabilities, so you can easily explore sort of virtual libraries of compounds and look for new optimization strategies. And Last of all, apologies, this is going to be quite a techie question here, but a couple people have asked it. And I should say, if we haven't answered your question, we will get back to you afterwards by email. So apologies, but I'm overrunning the time. But someone's also asked about the new Apple Macs with Apple Silicon, and does the new version of StarDrop support that? And the answer is yes. Apple threw a little bit of a curveball to lots of application developers, particularly with the new version of macOS. But I'm pleased to say that that StarDrop 7 works very nicely on Big Sur, and indeed we've tested it on the Apple Silicon chips. So you shouldn't have a problem with that, and the performance appears to be quite good. So hopefully that will help all of you Mac users out there. Well, again, thank you very much for attending. Just a reminder, we're going to be covering one of the other new features in StarDrop 7 in our next webinar. This is going to be looking at the new capability for reaction-based library enumeration. It's a great way to generate new virtual libraries based on tractable chemistry and reactions and available chemical building blocks. We're joined by our colleagues and friends at Molport, who are a compound sourcing company, and enable you to sort of search for the commercially available building blocks really easily, and then quickly enumerate and explore the resulting virtual libraries. So please come along to that. That's on Tuesday, the 23rd of February, and the links are on our website if you'd like to register. And last of all, that just leaves me to say a big thank you for coming along today, for staying a little bit over time. Just a reminder that the video of this will be available on our online community very soon. And in fact, those of you who go in the next couple of days will notice a big change in our website. We've got a whole new look and feel. So keep an eye out for that. That should be appearing real soon now. And please do explore lots of different videos of webinars, examples, hints and tips, and so on our online community. So again, thank you very much. And we look forward to seeing you again soon. Thanks again, Peter.
Pleasure. Thank you all.